Good morning. A warm welcome to you all to my physical chemistry class. Today I am going to discuss about the integrated rate expression for the various order. Last class I have mentioned about the differential rate expression. Okay. And the integrated rate expression is another rate expression which gives a direct answer to the value of k. That is, it gives what is k. That is the significance of the integrated rate expression. That is, the integrated rate expression gives the direct answer to k. What is k? Which is connected to the concentration of the reactant. It is usually derived from the differential rate expression by its integration, and hence it is called the integrated rate expression. Now we can start with the zero order reaction first. So we can now derive the integrated rate expression for zero order reaction. Zero order reaction. Okay. That is, a zero order reaction is that reaction in which the rate of the reaction is independent of the initial concentration of the reactant. Once again, I want to say the rate of the reaction is independent of the initial concentration of the reactant for a zero order reaction. That can be mathematically represented by considering a zero order reaction as, that is, A giving product. A giving product. If C is the concentration of A, then the differential rate expression, that is, starting is always from the differential rate expression, so the derivations always comes from the differential rate expression, that is minus dZA by dt, that is instantaneous differential rate equation, minus dZA by dt is equal to K into our definition. It is a reaction in which the rate is independent of the concentration of the reactant, that is K into Ca raised to 0. Any number raised to 0 is 1. So thus we have minus dCA by dt is equal to a constant k, the rate constant k. Okay. On rearranging this equation, we have minus dZA is equal to k into dt. K into dt. Okay. Then assume that consider a reactant substance of initial concentration A0 moles per liter. Okay. That the initial concentration of the reactant be A0 moles per liter. We have started a reaction with the A0 moles per liter of the substance A. Let X moles per liter have undergone a reaction at a time t. Okay. Then the concentration of the substance A remaining at the time, or the concentration of the substance A at the time t is A0 minus X. A0 minus X. So we can write that in the expression, that is minus dZA by dt is equal to K, can be replaced as, okay, minus dZA by dt can be replaced as the momentary rate or instantaneous rate of the reaction by substituting this minus d, Ca mean A0 minus X by dt is equal to K. Okay, it's equal to K. Now you rearrange the equation minus d A0 minus X is equal to K into dt. Okay, K into dt. Oh, sorry, I will explain. Okay, you please, before rearrangement, you do some mathematical work here. For opening this differential equation, we can write minus dA0 by dt minus plus dx by dt is equal to constant k. So now the equation now become minus dA0 by dt plus dx by dt is equal to k. Now the differential of a constant is always 0. Differential of a constant is always 0, also you know in the mathematics. So now our expression now become, this part becomes 0. Now our expression now become dx by dt is equal to k. Okay. Then rearrange this equation. On rearranging, that is dx is equal to k into dt. K into dt. So all the differential equation now reduced to this form. All the equation dx by dt is equal to that form will be obtained. So dx is equal to k into dt. Then going to integrate this expression. Integrating this expression, that is integral dx into k taken as a constant, k into integral dt. Now the answer is integral dx is x is equal to constant k into integral dt is t plus the integration constant I. Now x is equal to kt plus I. Now we want to find out the value of I, the integration constant. For that we have to apply the boundary condition. That is, the boundary condition is that in order to find out I, you have to make an assumption that when t is equal to 0, when the time t is equal to 0, then x is equal to 0. That is the boundary condition that we are applying. So we have 0 is equal to k into 0 plus I. Now I is equal to 0. Okay? Then substitute the value of I in the equation. Now we have x is equal to kt plus, in this equation substitute the value of I, kt plus 0, or x is equal to kt. Then you find out the value of k. That is the answer to the k. That is k is equal to x by t. This is the final equation for a zero order reaction. That is k is equal to x by t. That means x is the amount of the product formed. Is the amount of the product formed and t is the time. So x by t is nothing but the rate of formation of the product. So according to this, for a zero order reaction, the rate of formation of the product is a constant. That is, x by t is equal to a constant k. That is the equation. Then the